Good morning. So we're continuing our discussion today of entropy, and we're learning some new equations today called the Gibbs Equations. Very, 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 very important that as we start developing these relationships between different property values using entropy or isentropic relationships, that you understand they're only valid for certain situations. Okay, I've seen this on every exam that somebody goes to the equation sheet and they just find something that has pressure and temperature in it and they try to solve for their unknowns. Well, you can't do that. You have to know the conditions or the assumptions that are appropriate or valid before you can use certain equations. Okay, so as you write down an equation, please make note also of the situation under which it is valid, or the conditions under which it is valid. So as we develop these relationships, you'll find that they make it quite easy to analyze systems if we make the isentropic assumption. But of course, we can only make the isentropic assumption if we don't have, or we have very few irreversibilities in our system. Okay. We'll also talk about how, similar to assuming that something is 100% efficient, that the isentropic assumption allows us to look at best case scenario. Okay, so that's why we do it, that's why we analyze it, and that's why we have these relationships that have been developed using other property values. Homework 12 is due on Thursday. The brunt of the homework assignment is from this latter part of the lecture, or today's lecture versus last week's lecture. So please make sure that you've already gotten started on that you're understanding how the problems work. And again, pay attention today for which equations work in which scenario, because that will be pertinent to your homework. Just to review, that entropy can change due to two factors. The first is heat transfer. So if you add heat to a system, you will increase the entropy of the system, and if you remove heat from a system, you will decrease the entropy. And you can think of that, if you're unsure which one does which, that as you add heat to a system, the molecules begin to move around a lot more. So going, let's say, from a liquid to a gas, your molecules are more widely spaced, they're more erratic, more disorganized, they have more entropy associated with them. The second way to change entropy is during a process, is if there are irreversibilities of the process. So if there's friction or head loss or chemical changes, then you'll have an entropy change. And the entropy of a fixed substance won't change if you don't have irreversibilities and you don't have any heat transfer. So if it's reversible and adiabatic, we can also say that the process is isentropic, meaning that the entropy at state 1 is the same as the entropy at state 2. And you can have some situations where a process is isentropic, even though it's not reversible and adiabatic. But if it is reversible and adiabatic, it will always be isentropic, although the opposite doesn't always hold true, that there are some processes that have irreversibilities and heat transfer, but they counteract one another. So an isentropic process is one in which the delta S is equal to 0, or in other words, entropy 1 is equal to this entropy at state 2. And again, we're using this as the best case scenario, so we can approximate real devices as being isentropic if we want to know how effective or how efficient they might operate. So it gives us the minimum work input that is required for a system, or the maximum work output. And then again, a reversible adiabatic process is always isentropic, but the reverse is not necessarily always true. You need some other indicators to tell you whether or not it's isentropic. So recall that the entropy change of a reversible process was given by this equality. And note that it's a reversible process because it's S2 minus S1 is equal to del Q over T, the integral of del Q over T, and the inequality sign is gone. So the inequality sign is for the irreversible process. Equality is for a reversible process. So if we have an isothermal process, it's very easy to analyze this particular integral because we just take the T out from the integration. If it's constant, it's not changing. And then we just find the change in heat transfer. Well, if we don't know that the T is necessarily isothermal, we need to somehow have a relationship between heat transfer and temperature that allows us to analyze that integral in a functional way. Okay, we have tables where it's been tabulated. We can look up the change in entropy if we know initial and final states. But there are many cases where it's useful to us to be able to calculate it with some integration. So if we're looking to find that functional relationship between Q and T, there are some additional equations or scenarios that allow us to derive that relationship. So if we are to look at a simple compressible closed system, okay, the energy equation can be written in simple terms as the incremental change in heat transfer, that's a net heat transfer in, minus the integral in incremental change in work, that's reversible out, is equal to the change in internal energy of the system. Okay, so that's basically just Q in minus Q out plus work in minus work out equals U2 minus U1. But now we're just looking at it at each tiny little increment. So if we remember from the previous slide that we could rewrite this integration or this equality S2 minus S1 equals the integral of del Q over T, we can rewrite that as this del Q is equal to T ds. Okay, so that doesn't work. Del Q is equal to T ds. And we remember that del W is equal to P dV. Okay, so now we can substitute in T ds for del Q and P dV for del W, and we have this new relationship. T ds is equal to du plus P dV. So we have a relationship between entropy, temperature, internal energy, pressure, and volume. Okay, so it allows us to express properties in terms of other properties. And it also gives us a relationship that can be integrated in terms of T and the other property values. Okay, so TdS equals du plus PdV is called the first Gibbs equation. And this is an important one to note and remember. If we want to eliminate du from the equation, we can come up with an alternate expression. So we remember from before that enthalpy is equal to the internal energy plus pressure times specific volume. So if we take the derivative of this and we find dH is equal to du plus PdV plus VdP, because we need to take the two-part derivative of that. So we could rearrange that in terms of du and say, well, du is equal to dH minus PdV minus VdP. And if we substitute that back into our original equation, this TdS is equal to du plus PdV, this one, then we can have, now instead of internal energy in our equation, we can have it in terms of enthalpy. Okay, so these two equations are equivalent, and they're called Gibbs first and second equation. Okay, so we can rewrite it in another form. We can solve for ds, and then if we integrate, then we'll have this integral of du over t plus pdv over t dt. Okay, so although these were derived using the reversible equality, they're valid for simple compressible systems that are open or closed, and the process can be reversible or irreversible. So we can use this entropy relationship in terms of other property values for any system. Okay. Liquids and solids can be approximated as incompressible, meaning that their density does not change. They cannot be compressed, or their specific volume doesn't change as well, which is the reciprocal of density. So then that reduces the first Gibbs equation, ds, instead of being du over t plus dv over t, pdv over t, this one. This term goes to 0 because dv is approximately 0. So we have ds is equal to du over t, which we can then rewrite if we remember that internal energy is equal to C times T, or C sub P, C sub V, but for a solid or a liquid, there's just one term, it's only C. Then we can have this additional form of the Gibbs equation, which allows us to calculate the entropy change of liquids and solids. And you note that it's dependent solely on temperature. Okay, we don't have to worry about pressure. We don't have to worry about volume in this particular case. So we can approximate this if we calculate this integral. The integral of dt over t is natural log of T2 over T1, that the entropy change of a liquid or solid can be approximated in this way. So again, if it's an incompressible substance, we can use this equation. This is not valid for saturated liquid vapor mixtures. It's not valid for gases. Okay, only liquids or solids that can be approximated as incompressible. And that is because this dV term has to go to 0 in order for us to come up with the equation like this. Okay. So the entropy change of a truly incompressible substance is dependent on temperature only. Okay, specific heat and the temperature. And if this were to be an isentropic process, we would note that the only way that this particular term can go to 0 is if T2 is equal to T1. So for an isentropic process of an incompressible substance, it also has to be isothermal. Okay, so in order for this equation to be satisfied, isentropic for an incompressible substance also means that it's necessarily isothermal. Okay, again, this is only valid for incompressible substances, so solids and liquids that aren't close to the vapor region at all. So let's do an example of this. We're going to use the properties of liquid methane, and there's a table in your textbook. It's on page 350 that gives the properties of liquid methane. So it's not in the appendix, it's actually in the chapter itself, chapter 7. And we're going to calculate it two ways. We're going to just use the tabulated values, and then we're going to use the incompressible approximation. And we'll see what is the percent error in treating methane, liquid methane, as an incompressible substance. Okay, so methane, as it undergoes a process from 110 Kelvin and 1 megapascal, so that's this line here, so 110 Kelvin and 1.0 megapascals, to 120 Kelvin and 5 megapascals. So here's 120 Kelvin, here's 5 megapascals. So quickly calculate, using the tabulated values, what is the entropy change of that liquid. Using which formula? Well, first we're using the tables, right? So we're just looking up the properties at 110 and 1 megapascal and 120 and 5 megapascal. So there's a column for entropy here. So we'll need to calculate using the tables. 0.27. Okay, so delta S is equal to the entropy at state 2, which is 120 K and 5 megapascals, 5.145 kilojoules per kilogram Kelvin, minus 4.875, that's the entropy at state 1, kilojoules per kilogram Kelvin. So that equals 0.27 kilojoules per kilogram Kelvin. Okay, that's part A. So part B now, if we're using the equation from the previous slide, what would we need to do first before we just simply apply that equation? Because we're dealing with methane at 2 different temperatures, 2 different pressures. Okay, we need to find the C average, so we can do that 2 different ways. Well, the best way to do it is look at it at each case and then calculate the average. So C of 110K and 1 megapascal is 3.471 kilojoules per kilogram Kelvin. And then the C at the second case is 3.486. So this 3.471 plus 3.486 divided by 2 gives us 3.4785. kilojoules per kilogram Kelvin. So then we can use our equation where delta S is equal to C natural log of T2 over T1, where the C is the average value from those two different states. Yeah, 0.3. So 3.4875 kilojoules per kilogram Kelvin multiplied by the natural log of 120 Kelvin over 110 Kelvin is equal to 0.303 kilojoules per kilogram Kelvin. So we calculate the percent error. It's the absolute value of our actual minus our predicted divided by the actual value. So 0.27 minus 0.303 over 0.27. And we get that the error is about 12.22%. Okay, 12% error, is that acceptable? Is that pretty high? That's pretty high, especially when you have a table to calculate it. The reason for this is that the critical point temperature of methane is 119 Kelvin. Okay, so what happens at the critical point? Do you remember? It changes state and it goes directly from a liquid to a vapor without really going through a phase change process. Okay, so weird stuff happens around the critical point. If you're ever calculating property values near the critical point and you're using assumptions like incompressible assumption or I don't know, some other, an ideal gas assumption or something like that, if you're near the critical point, your values will be off significantly because weird stuff happens there. It doesn't follow the same properties, the same, you know what I'm trying to say. It doesn't follow suit. It doesn't act like a liquid. It doesn't really act like a gas. It's kind of in between. So we have a little bit higher error in using it there. Okay, any questions on this example? So again, what is an incompressible substance? Yeah, the density or the specific volume is not changing with temperature or pressure. Okay, so undergoing whatever process or the initial and final states of your process, that the specific volume and the density won't change. So let's look at this table. Does our density change from 110 Kelvin to 120? So our initial density, what is it? Right there, 425.8. Our final density, 415.2. Okay, it changes, right? So we should expect that we would have some error in making an incompressible assumption for a substance that's not actually incompressible.
So between these, so 0.27 and 0.033, that's the delta S in each case, right?
Yes.
Okay.
Yeah. So this is the actual value, and this is the value making the incompressible assumption. Because by using this equation, you're assuming that your fluid is incompressible. Because this is only valid for incompressible substances.
So is there one that's more valid, or you would want to use one or the other? Or
well, you would, if you have a table, use a table. If you have a table and you know the initial and final pressure and temperature, it's easiest to use a table or use Ease or some other software program. If you don't know the final temperature or you don't know the final pressure, then you can say, okay, I'm going to make an incompressible approximation. Use that to calculate a final temperature, you know, going through the system. Maybe you calculate delta S, you see what S2 would be, go back to the table, look it up, and see what your temperature would be at that. And then you say, okay, was my assumption valid? And if you see that the temperature that you're at is no longer an incompressible substance, then you can say, okay, well, maybe I can't use that equation. I need to find a different equation. And like the Gibbs equation, if you're not dealing with something that's incompressible, then you have to take into account the pressure times the change in volume. So, okay, any other questions? All right, so let's talk about ideal gases. So again, remember, this is a specific case where these equations apply. So if we look again at the first Gibbs equation, we notice some terms that come up often when we're dealing with ideal gases, right? So we can substitute du with c sub v dt. And this pdv term, we're going to substitute with, well, the pdv over t, we're going to change it to p equal, because p equals rt over v, we can substitute with r dv over v. So this gives us an additional relationship that we can use where maybe we know the R value and we know the change in volume. If we don't know pressure, we don't know maybe the internal energy change, but we know how the temperature changes and how the volume changes of our substance, then it's very easy to calculate the change in entropy for an ideal gas. Okay, so we have to calculate, again, this integral. So the integral of dt over t is just going to be the natural log of T2 over T1, and then this integral, R natural log of V2 over V1. If V is not dependent on T, then it comes out easily. Otherwise, we need to know maybe the relationship. So similarly, we can do the same thing with the second Gibbs equation. So instead of having a du here, we have a dH. So it comes out looking very similar, but this time maybe we know pressure and temperature, and we don't know specific volume. So if you know certain conditions about your system at state 1 and state 2, let's say pressure is easy to measure, so it's known, then we can use the second Gibbs equation. Okay, if we, instead of knowing pressure, we know volume, we would use the first Gibbs equation, because they're both valid for ideal gas processes. Now again, they're very specific to this case of an ideal gas. Just like the previous derivation was only for incompressible substances, we have to be very careful about when we try to apply these equations. Because this does not work for a liquid. Okay, you've made the assumption it's an ideal gas and substituted in that P is equal to RT over V in order to come up with this equation at the end. Okay. All right, so we can come up with those two. Again, they're derivations of the Gibbs equation that are specific to ideal gases. Okay, so keep that in mind. Now we can make, of course, the constant specific heat assumption. So we just find the constant average specific heat in either case. Then instead of needing to know the functional relationship between C sub P and T, we just have this relationship where we use some average C sub P. And there will be some problems on your homework where you don't necessarily know the final temperature and you have to kind of guess and say, okay, I don't know the final temperature, so I'm going to find an average C sub P at some value. I'm going to assume maybe the temperature changes by this much. And we'll do an example of that in class 2. So then you say, okay, if I make that assumption and I calculate this, I solve for the final temperature, now I'm left with, this T2 is equal to, let's say I assume T2 was 500 and it ends up being 480. Then I can say, okay, well, I'm going to recalculate, find a new C sub P, and see if my final temperature value changes significantly. Okay, or you can say, well, it's pretty close. Using C sub P at 480 versus 500 as the final temperature is so similar that it's not going to make a large difference in the final calculation. Okay, so sometimes that is an assumption that you have to make. If you don't know the final temperature, you can't calculate an average if you don't know the final, so you have to kind of guess, use an educated guess, and then in the end, you see if your guess was close enough. So again, constant average specific heats, we've talked about that in previous classes. Hopefully you understand how it works, how to solve for it. We're going to assume. If we can't make that assumption, if we know a functional relationship between C sub P and T, we can actually calculate that integral. And there are some properties of, there are some substances for which we know that functional relationship between C sub P and T, and they've been tabulated. Okay, so if we look at table A17 for air, If you have your book, go ahead and look at it. Because we've previously used this table to look up internal energy and enthalpy, but there's a couple of other columns in this table that we haven't used, like P sub r, V sub r, and this S superscript 0. Okay, this S superscript 0 is not entropy. It's this integration here, the integral of C sub P as a function of temperature times dt over T. Okay, so instead of calculating this integral every time, for certain substances we know that functional relationship and it's been tabulated, so we can replace this integral with the value that's in this table. Okay, similarly, if we want that change in entropy from state 1 to state 2, this S sub 0 is calculating it based as 0, using 0 as the base point. So if we want to know this delta S, or this functional change as we go from some intermediate temperature, not T equals 0, but some intermediate temperature 1 to state 2, then it's just this S superscript 0 minus S superscript 0 subscript 1. Lots of super and subscripts there. Okay, so it's a function of temperature only, just like internal energy and enthalpy, but entropy itself for an ideal gas is a function of temperature, pressure, and specific volume. Okay, so when we're calculating this reduced entropy, which is another way of talking about it, it's only a function of temperature because it's a function of C sub P and T, which C sub P is a function of temperature and T is a function of temperature. But instead of using this equation for C sub P, which if you remember is quite long and has a lot of variables associated with it, we can just use the tabulated values and calculate it. Yes? So there are some problems that you have on homework that will say calculate the change in entropy using, for an ideal gas, using the average specific heats or variable specific heats. So if it's variable specific heat, then you have to actually just use this, and then it'll say compare to the tabulated values. So you would calculate it 3 different ways. You would calculate it just using one of these equations and assume some average specific heat that you would calculate based on temperature. And again, if your temperature is not known, then you have to guess and then see if your guess was accurate. Then there would be a second phase where it says, okay, using the variable specific heats, in which case you'd have to go to the table to look up these values and then substitute in the equation, see how close it is. And then if you were to just use the table itself, you would just find S2 and S1 for the ideal gas. And in this case, we don't have a table for ideal gas that shows entropy change because most other properties are only a function of temperature, but it's a function of pressure and volume as well. So there'd have to be a separate table that looks similar to water tables in order to look up entropy values. So let's do an example. So we're going to do one ideal gas specific heat problem, and we're going to assume constant specific heats and variable specific heats. So we're going to look at it 2 different ways and calculate this change in entropy based on those 2 different assumptions. Okay, so air is an ideal gas. That's good. We have an insulated piston cylinder device with 300 liters of air at 120 kilopascals and 17 Celsius. The air is now heated for 15 minutes by a 200-watt resistance heater placed inside the cylinder. Determine the entropy change of the air assuming constant specific heats and variable specific heats. Okay, so there are a couple of assumptions that we can make or conclusions that we can draw from this particular setup. So just in the first couple of lines, what information do we learn? Be careful about that. It's not isothermal. No heat transfer, okay? So adiabatic is different from isothermal. Adiabatic means no heat transfer, but just because there's no heat transfer doesn't mean that the temperature stays the same. So be very careful about that assumption. So yes, insulated piston cylinder device means that there is no heat transfer to the surroundings, but you can see there's a resistance heater in there, so the temperature of this should increase, right? And the volume will probably increase, but the pressure should remain the same because there's no external forces being applied to that piston. Okay, so an ideal gas in a piston cylinder device, so the pressure will remain constant, temperature will increase, volume will increase. That's what we should expect to happen during this problem. So how do we set this up and start solving? What is some additional information that we need in order to do this? Okay, so I guess we have to define our system, right? So what are we dealing with? It's a closed system. Okay, so if we were to do the closed system energy balance, we have Q in minus Q out plus work in minus work out is equal to M times U2 minus U1. Okay, do we have any heat transfer? Do we have any work in? Do we have work out? Yes. What kind? We have electrical work in, and what is the work out? Boundary work. Okay, minus boundary work out is equal to M times U2 minus U1. And then we can combine this term with the boundary work because it's a constant pressure problem. It's going to be P times V minus P delta V. So we move it over to this side of the equation. So the electrical work in is equal to M times H2 minus H1 because we've combined the boundary work with our change in internal energy on that side of the equation. Which we can rewrite as M C sub P times T2 minus T1. Okay, that's an alternate. Okay, do we know our electrical work in? Okay, we can calculate it, right? We're given all the information to calculate it, so this is going to be a known. Do we know the mass? Yeah, so we don't know the mass, but we do know the volume, and we can figure out from the ideal gas equation the mass. So we can calculate that. And then do we know this C sub P and T2 and T1? We don't know T2 yet. We know T1. We're going to need T2 to figure out C sub P. So this is a case where we're going to have to make an educated guess and see how close or how accurate our guess was. Okay, so let's solve for the electrical work in. We have a 200-watt resistance heater that is on for 15 minutes. So this electrical work in is going to be equal to the power multiplied by the time period. So this is like voltage times current times time. So 15 minutes, which there's 60 seconds in 1 minute, right? My brain is foggy today because of allergy medicine. Just apologize in advance for that. So this is 180, remembering that a watt is a joule per second, so this would be the same as 0.2 kilowatts or 0.2 kilojoules per second multiplied by 15 minutes multiplied by 60 seconds. It gives us 180 kilojoules is our electrical work in. And then our mass, if PV is equal to MRT, our mass is equal to PV over RT, and we know the initial pressure, volume, temperature, and we can look up R. So we find that it's 120 kilopascals times 0.3 meters cubed divided by 0.2870 kilojoules per kilogram Kelvin multiplied by the temperature. So do we use 17 Celsius or do we need to convert? Have to convert it to Kelvin, so it's 290 Kelvin. So we find our mass is equal to 0.4325 kilograms. Okay, so we know this term, we know this term. We're going to have to guess a final temperature to find C sub P and then solve for T2. And then we'll see how close we were to our guess. So if we look at the tables, table A1, I think, for C sub P, let's see, for air, table A2B, our current temperature is 290 Kelvin, which is pretty close to 300 Kelvin. So C sub P is 1.005. And then it just continues to increase from there. Up to 450 Kelvin is 1.02. Up to 800 Kelvin is 1.099. So we have to make an approximation. What do you think our final temperature will be inside that cylinder? So 15 minutes with 0.3 meters cubed. That's not very big, not a very big cylinder. This 1 kilojoule heater is on for 15 minutes. Do you think the temperature will increase by a lot, a little? Probably a lot. I know the final answer, but I would say that it would at least get up to, 300 Celsius. That it's going to be, if you think about the temperature, it's going to be significant. Okay, so let's just assume that our C sub P is going to be, our C sub P average is going to be somewhere around like 400 or 450 Kelvin. Okay, so we look up C sub P at 450 Kelvin, and then we're going to say, okay, after we've calculated our final temperature, we're going to go back and check and see if our assumption was close, okay, or our approximation was close. So then we go back to this equation and we solve for T2. So T2 is equal to this work electrical in divided by M times C sub P plus T1. And if we plug in the numbers for that, 180 kilojoules divided by 0.4325 kilograms. And then C sub P, we're going to just choose the value of 1.02 kilojoules per kilogram Kelvin plus T1. And T1 initially is 290 Kelvin. So we solve for this T2 and we find that it is 698 Kelvin. So then we say, okay, what would be our average temperature? 698 plus 290 over 2. That gives us an average of some value. Calculate that. Fast fingers. Who has fast fingers?
I have a question.
Yes.
How do you know the time average?
For C sub P?
Well, no, like how you're doing the 698 plus 290. How do you know to do it?
I'm comparing it to my assumed average. So I looked up C sub P at 450K. So right now I'm going to calculate this temperature. So what is the actual average temperature? 698 plus 290 over 2? 494. Okay, what would be C sub P at 494 Kelvin? It's close to 500, 1.029. Okay, so I could redo this calculation using 1.029 and find a new temperature, but 298 or 698, that's pretty close. Okay, it's not going to change significantly from what it was before. So we're going to say, okay, my assumption was pretty good. That's okay. I'm going to use that value. 290 is the initial temperature, 17 Celsius. Yeah. Okay, so this whole process here was just to find our final temperature. We haven't even started calculating our entropy change yet. Okay, so we have to do it two different ways. In part A, we're going to use constant specific heat. In part B, variable specific heat. Oh, I hate whatever it is they're using on this board. So if you're a really bad guesser and then you come back here, let's say you guess something and you find your final value is like 500 and you calculate your average and your average is way off from where you assumed your C sub P, then you need to do it again. So let's say you are a really bad guesser and you're like, I think the temperature is going to decrease.
You're saying that once we find 698 Kelvin, we find the average temperature, you're comparing that C sub P at the temperature close to that one to what we assume is how much difference needed?
You're assuming a temperature to find C sub P. You're not assuming a temperature to use that temperature. So C sub P is used to calculate your final temperature. So let's just redo this calculation. Let's use, instead of 1.02, use 1.03 and tell me how different it is. Plus 290. So if this is 1.03, then we get what? 694. So it was a pretty good guess. 694, 698, that's not going to significantly change our calculations when we start doing the approximations. So it's an okay number to use. But if, let's just say you calculated this and you saw that instead of being 1.02, your C sub P should be 1.9. That's just a random number thrown out there. Then when you recalculate your temperature, you're going to have a very different value. Then you need to use your new value. And then you may need to do one more iteration, because the further you are from the initial, if the further your initial guess is from the actual value, the more iterations you may have to do to refine it and get it closer. But 698, 694, that's close enough. So as you do this on your homework, you're going to have to make educated guesses to try to solve for it. But okay, so we found our final temperature, and we're okay with that value. And again, when I'm grading the homework, if you have a reasonable value, then, it's going to be okay. And you shouldn't expect that you should have the exact same answers as the textbook if you're guessing values too. And when you do have the exact same answers, that's when I get suspicious. So just so you know. All right, so part A, delta S is equal to S2 minus S1, which, if we're using the constant specific heat approximation, that means the constant average specific heat, so it's an approximation rather than looking it up in the tables. Then we have M times C sub P, natural log of T2 over T1, minus R, natural log of P2 over P1. So if we start putting in the values for that, again, we can use this same C sub P and the same T2 that we found earlier because we were close enough. If we were super far off, we wouldn't be able to use that same value. So 0.4325 times 1.02 kilojoules per kilogram Kelvin. This is kilograms. Natural log of T2, and again, you have to use Kelvin, which is 698 over T1, which is 290, minus R, natural log of P2 over P1. And I'm not putting in the values for that because P2 equals P1, so that term is going to 0. Because P2 equals P1, this is natural log of 1. Natural log of 1 is equal to 0. So anytime you have an isothermal process or an isobaric process, these terms will go away, one or the other. If they both go away, that means it's also isentropic. There's no entropy change. But if it's an isobaric process, that term goes away. It's an isothermal process, that term goes away. So then we're left with delta S is equal to the total entropy change, 0.3875 kilojoules per Kelvin.
What table do you use to look
at? Table A to B. Yeah, that's from A to B. I'd have to look at that. I haven't done the homework yet, so.
I'm so confused. So you start guessing?
You make not randomly guessing, you make an educated guess. So you'll say, okay, you know, I've looked at examples in the text. I remember some of the examples in class. You know, for some piston cylinder device with a heater in it, the temperature increased by 600 Kelvin. Okay, so I'm going to guess that maybe that'll happen too. Use a number kind of in the middle. You know, you have to use a little bit of logic doing it, but then in the end, you double check your guess. And you say, okay, I guessed this. How close was my guess? Oh, it was way off. I need to redo this again with using this new T I've calculated, calculating the average, finding that new C sub P, calculate it again, and see how much the temperature changes. Then you may need to do it one more time depending on how far off you were. Yes?
This could be like a pretty common practice, like a common technique we see.
Oh, yes.
Like my concern is I'm just going to see it and not know whether I should guess or whether I'm missing something.
I'll have to look at the homework problems and see which ones you might have to guess on, but
I'm just assuming that I'll know there's some chart that I don't know to look at.
well, this is not just specific to these types of problems. All the time in engineering, you don't know the final answer, and you say, okay, well, if it's this, what's going to happen? And I'm going to calculate and see. Okay, I assumed it was this. I ended up calculating that it's this, so I need to fix my assumption. Okay, so that's an optimization process that's very common, and it's good to recognize that happens in engineering a lot because, you know, we don't often know the final temperature. We have to guess, then we run a scenario, and then we figure out, oh, okay, I was running the scenario based on what I thought, but really it's this, and then redo it. But that happens a lot.
So do you always start guessing when a T2 is not given?
If you're trying to use a constant specific heat approximation, you have two unknowns, right? C sub P and T. Really, it's one unknown because C sub P depends on T. So you have to just make a guess and then calculate your T and see if your guess was okay.
Yeah, yes. I guess on this one.
Hint, you need to guess a T. I'm not going to do an exam problem where you have to guess a final temperature. You guys, some people like to guess anyway on exam problems, but that won't be the case. I'm not going to require you to iterate a bunch of times on an exam because I don't think that's testing your knowledge of the material. It's testing your ability to not screw up your algebra during an exam, which that's when everybody does screw up. Simple math is during exams because you're stressed or whatever, and so I try to be lenient about that. I don't want to test math skills on the exam necessarily. You should have some basic ones, but I want to test your understanding of concepts and principles that apply to thermodynamics. Okay. Moving on. Okay. So this is again the constant specific heat approximation. So we're assuming some constant average specific heat. Okay, so now for part B, we're saying, all right, I'm not going to assume that there's some average specific heat. I'm going to assume that specific heat changes with temperature, and I need to have that functional relationship worked out. So we go back to our energy balance. Okay, so previously with specific heats being allowed to change, we said, okay, I'm going to say that H2 minus H1 is equal to the C sub P times T2 minus T1. Well, now instead of doing that, I'm going to use this equation and look up H2 and H1 in the property tables and find the actual temperature. So if I calculate H2 from that equation, So this is part B. I calculate H2 from that equation. I find that it's equal to 706.34 kilograms. So then I use that to find this S2 superscript. So through interpolation, I've calculated H2 as 706.34. So then I go to the table and say, okay, where, table A17, where does H2 for air, I'm in the English tables, equal this value? So if I go, okay, it's in between 690 and 700 Kelvin, right? So then I use interpolation to find now my S superscript value, which I find to be 2.5628 kilojoules per kilogram Kelvin. So now delta S for variable specific heats, the equation for that is mass times S2 superscript minus S1 superscript plus R, natural log of P2 over P1. Okay, where again, this value here is equal to the integral of C sub P as a function of T times dt over T. Okay, oh, dt over T, something like that, right? Okay, so instead of having to calculate this integral and know the functional relationship between C sub P and T, I go to the tabulated values for it, look up S superscript 0 subscript 2, which is found because I determined H2 from that original equation. And then again, P2 over P1, if our pressure is constant, this term goes to 0. So we just need to know the tabulated values of this S2 and S1. So delta S for a constant pressure process is equal to the same change in entropy if it were just the reduced entropy values. So we find that it's 0.4325 kilograms multiplied by S superscript 0 subscript 2, 2.5628 kilojoules per kilogram Kelvin minus 1.66802 kilojoules per kilogram Kelvin. So we find delta S to be equal to 0.387 kilojoules per Kelvin. Very similar to what we calculated in part A. Okay, does that make sense? Are there still any other questions about finding the final temperature and using it and that sort of stuff? From the table, so it's at 290 Kelvin, the value. So this is at the temperature that it equates to this same enthalpy, which I didn't directly calculate the temperature because I don't need temperature, I just need S2. So if you interpolate, you know, you do like H2 minus HA over HB minus HA is equal to S2 minus SA over B minus SA, something like that. And then you solve for that value. Or you use your interpolation function on the calculator if you know how to use it and it's accurate. I don't care if you do that. Just say by interpolation. That I don't expect necessarily to see this every time you interpolate. Yes? You solve for this one? Oh, it's fine. As long as it's in the same place here. Yeah, so if this is down here and this is down here, then that's okay. The thing that matters is that this one and this one are in the same place. So this could be like, this could be H2 minus HB over HA minus HB. I mean, you can rearrange this stuff all around as long as this is in the same place and like the equivalent other stuff's in the same place. If that makes sense. Because if you start mixing everything around, it's not going to work. But yeah, they have to translate correctly over. That's not embarrassing. No, as long as it's in the right place, then you're fine. It can be anywhere. It can be any of these 4 spots, as long as everything else matches up. Okay, any other questions? Yes? Kilojoules per kilogram, sorry. Kilojoules per kilogram. No, it's not a mass, sorry. No, H2 was solved using this equation. So H2, I can write that out. H2 is equal to the electrical work in divided by the mass plus H1. It was solved. And then using that solved value, we interpolate to find the equivalent value on the same line of the table for this S02. SO2, I don't know what to call it. I hate trying to speak superscript and subscript. It's a lot of extra stuff to say. Okay, any other questions on this? All right. Now, we have additional assumptions or approximations that we can make to refine these equations even further for very specific cases. So if we want to say that there is no change in entropy or it's an isentropic process, we can set both sides of the equations equal to one another. So in all of these relations that we're solving for a change in entropy, if we say, okay, there is no change in entropy, now we can set the 2 sides of the equation equal to one another and then come up with additional tools for analyzing and determining final property values. So these have all been derived in the text, and again, they're obtained by using this idea that if our entropy is constant, then these 2 sides of the equation will be equal to one another. So again, these are only valid for ideal gases, constant entropy, and then there are additional problems where maybe we can look at incompressible substances. But as we change those, manipulate those, then we come up with these relationships as well. Valid only for certain conditions. So let's do an example with an ideal gas in a compressor, and now we're assuming that it's an isentropic process, so we can use some of these other relationships. So instead of solving for the change in entropy, maybe we use that to solve for final property values, which are unknown. And again, we can only do this for ideal gases, and we can only use those relationships if it's an isentropic process. So if we're saying it's isentropic, in essence, we're saying that there are no irreversibilities, probably that there is no heat transfer. Okay, so an isentropic process will be approximately that. Okay, air is compressed in an isentropic compressor from 15 psia and 70 Fahrenheit to 200 psia. Determine the outlet temperature and the work consumed by this compressor per unit mass of air. So work consumed is going to be the minimum work required for these same inlet and outlet conditions, because we're assuming it's isentropic. Okay, so, and making an assumption that it's isentropic does not necessarily mean that it's isothermal, particularly for an ideal gas. Okay, because ideal gas, although internal energy and enthalpy depend on temperature only, entropy is not that way. Okay, so it depends on temperature and pressure and specific volume. So it's not necessarily isothermal, and we'll find it won't be isothermal in this case. Okay, so we know the initial and final pressure but we need to determine the outlet temperature. So what's one way that we can do that using what we just learned on the previous slide? Were there any relationships that relate temperature and pressure? The middle one. Okay, so T2 over T1 is equal to P2 over P1 to the K minus 1 over K. And what's K? Yeah, it's the specific heat ratio. So K minus 1 over K. And we get those, that's the same, that's a K. Okay, we get those again from table A to B. A to B for ideal gases. Okay, so this is a similar situation. We don't know the final temperature. So we're going to have to guess a K value or guess a final T2 temperature to solve this equation to find T2. Okay, so because T2 is an unknown, if we're looking for a K value at some average medium place, then we have to do that. Okay, so what do you think would be a good assumption for our K value? And we have to be in the English tables, although it doesn't matter for K. K is 500 or T is? T is 500 what? Fahrenheit? Okay. Yeah, okay. For a compressor, all right. So let's use, if we use 500 and our initial temperature is 70, what would our K value be? A2E. A2EB, page 950. That would be the K at 700, but we want to use an average value. So we have to find the average between 70 Fahrenheit and 700 Fahrenheit or 600, whatever value we choose. Finding K. So an average K, a good average K would be about 1.39. If we look on this table, even if we don't know our final temperature, we're kind of looking at it and say, okay, my average is going to be somewhere probably in the 400, 500 range. Let's just use 1.39 as our average value because that's a pretty good guess. All right. So T2 is equal to P2 over P1 to the K minus 1 over K multiplied by T1. So P2 is 200 PSIA. P1 is 15 PSIA. We're going to use K as 1.39, so 1.39 minus 1 over 1.39 multiplied by T1. T1 is in terms of Fahrenheit. What does it need to be? Rankine, right? Not Kelvin, not convert to Celsius and then convert to Kelvin, not convert to Kelvin. Just convert it to Rankine. Okay, so Rankine would be 530. What? Oh, what do I add to 460? Yeah, I think it's 4. Okay. Okay. So 530 Rankine. So if we calculate this, then we find it's 1096 Rankine, which is equivalent to 636.2 degrees Fahrenheit. Okay, so if we go back to this table and we say, okay, if I'm actually at 636 and I assumed that my average value was between like around 400, then we can calculate the average, right? So 636.2 plus 70 over 2 gives us what as our average value? What's the value? 636.2 plus 70 over 2. 353. Okay, so if we go back to the table and say, okay, at 353.1 is 1.39 a pretty good approximation? Yeah, that's good. All right, so our K value is fine. We don't need to change it. Now we're actually trying to find the work per unit mass of air that's consumed by the compressor, so we can perform an energy balance. Q in minus Q out plus work in minus work out is equal to M, oh no, not M, just H2 minus H1, because it's per unit mass. So lowercase q, lowercase w is equal to H2 minus H1. It's an isentropic compressor. We're going to assume that because it's isentropic, it's reversible and adiabatic. Okay, that's not always the case, but they haven't given us any other information to assume otherwise. So we're just going to assume it's reversible and adiabatic. So there's no Q in, no Q out, no work out because it's a work consuming device. So work in is equal to H2 minus H1, which is equal to C sub P times T2 minus T1. So C sub P is 0.244 BTUs per pound mass Rankine times 1096 minus 530 Rankine. So we get 138.1 BTUs per pound mass is our work into the compressor. So we found T2, we found our work in. We could also use the tables and look up H2 and H1 for air, and we would find a pretty similar answer. Okay.
Okay, so where do you find 1.39 for the K?
So look in
No, I understand
that.
that.
Yeah.
But like, how do you know it's like?
Okay, so you don't know initially. You say, I'm starting at 70 degrees. How high is the temperature going to go? I don't really know, but my understanding from previous problems is, let's say it increases by 600 degrees. So then you say, okay, I'm starting at 70, I go up to 700. Then you look at those two lines on the table and you find the average in between. So like the average between 1.4 and 1.377, we'll say, okay, let's just use 1.39. Then you go through, you calculate, and you solve for your temperature. And you look at that temperature and you say, okay, my actual temperature is this. I'm going to now calculate the average temperature and look up K at that temperature and see how close I was initially. If you're close enough, you just use it. If you're pretty far off, you have to redo your calculation. Yeah. Yeah, but I mean, it's not interpolation, it's just average, right? So, well, I mean, yeah. Yeah, the average, well, you can do it either way. Yeah. So you can either look it up at the average temperature or average the C sub P values. Any other questions on that? Oh, we still have some stuff. Okay, so you can do the exact analysis. So if you set these equations equal to 0, then you can say that this S2 minus S1 is equal, or S2 is equal to S1 plus R natural log of P2 over P1. So if you don't have the second state, you can use this for an isentropic process. And then these relative pressures also come into play because we can rearrange these equations and find this P2 over P1, which we used a long time ago when we were calculating our Z values to find a reduced pressure. So then we say, okay, this P2 over P1 is going to be equivalent to the ratio of these two reduced pressures. And again, this also helps you to find the second state when it is unknown. If you know how the pressure changes, then you can look up the reduced pressures, and the ratio of those reduced pressures should be the same for an isentropic process. Same thing for a specific volume. It's an equivalent approach. So there's an example I didn't get to. Okay. I will post this example so you can look through it because it might be helpful for you on your homework. And if you have any questions, please email, get working on that because if you wait till 10 p.m. on Wednesday night, I'm probably not going to answer any questions. I'll be asleep.